So week 2 of Physics 157 will deal with chapter 3 in the textbook and will be about two-dimensional kinematics. So the first thing they'll talk about is vectors. And we will just be working in 2 dimensions. So we'll have our XY coordinate system, and any vector A can be broken into what are called the components, which are AX and AY. And this involves simple trigonometry, Pythagorean theorem that the magnitude or the length of the A vector is the square root of the X component squared and the Y component squared. The angle theta can be found using tan AY over AX. And the components can be found, once again, just basic trig. AX is the length of A times the cosine of theta, and AY is the length of A times the sine of theta. So you will have some problems on mastering physics that you'll have to answer about finding components, or given components, finding magnitudes and directions. So remember, this stands for magnitude. That means the length of the vector. And the direction, conventionally, this theta is starting at the x-axis and going counterclockwise. And your calculator will understand that, which way. If you put an angle theta of, say, 160 degrees, your calculator will know that you're over here at 160 degrees. Okay, so you'll have some problems to practice in mastering physics of using just those simple definitions. And then they'll start applying this two-dimensional motion to kinematics. So projectile motion is the first obvious application of two-dimensional motion. So this is an object in free fall, but now it is allowed to go in 2 dimensions. So like if you kick a football and it goes like this, that's a projectile. Or if you throw something off a bridge and it goes like this into the water, that's a projectile. And there are some very good videos about this motion. The thing to remember is that in the X and Y directions of its motion, you can analyze the kinematics separately. And in the X direction, there is no acceleration. So there's no force sideways on these objects. There is only the force of gravity, which causes its Y direction acceleration to always, always, always be negative 9.8. All the kinematic equations then apply in each direction. And because there's no acceleration here, really the only kinematic equation here is that this is Vx initial times t. The 1/2 at squared is not there because there is no acceleration in the x direction. But then all the other equations over here apply as well. So Vf is Vi plus At is a very handy one. And delta y is Vit plus 1/2 At squared. Now this Vi, this is Viy. And Viy is the component of the velocity vector in the y direction. Similarly, this Vxi is the component of the initial velocity vector in the x direction. And so those equations will basically allow you to solve these projectile motion problems. There's some excellent videos on mastering physics that you can watch, some examples of how to do that. And then the notes on the D2L PowerPoint slides are also really good. The next kind of two-dimensional motion that you'll look at will be circular motion. And so this means something going in a circle. Now its velocity, even if its speed is constant, the velocity vector is changing because it's changing direction. And so this thing is accelerating. And the acceleration is toward the center of the circle always. It's called the centripetal acceleration. And that is simply the acceleration due to the changing direction of the velocity vector. Its magnitude doesn't change because the magnitude of velocity doesn't change. And the formula for the centripetal acceleration is v squared over r, where r is the radius of the circle. So you'll have a number of problems where you simply have to work out perhaps the radius given the acceleration and speed, or any combination of using that equation. So this r is radius of circle. And this is called centripetal. Centripetal means center seeking, not to be confused with centrifugal, which is a fictitious kind of force, and we're not going to talk about that here. So this is centripetal acceleration. Sometimes it's called radial acceleration. I think your textbook sticks to centripetal acceleration. Okay, the next kind of two-dimensional motion that you'll see in this chapter is motion down a ramp. Now, in fact, it's one-dimensional motion, but the fact that the ramp is tilted means you do have to use some components. That's why they're putting it in this chapter. So motion down a ramp. And the thing you have to know about motion down a ramp is, in the absence of friction, it is gravity pulling the object down the ramp. But it is not just negative 9.8, the acceleration. Because what we do here on a ramp is we make the x and y axes tilted so that the object is actually moving in the x direction, and it will accelerate down this ramp, not at negative 9.8, but it will accelerate down the ramp. Now, the way we've done it with x to the right, this is going to give us a positive x direction acceleration. And the way that you figure it out is you take the acceleration vector due to gravity, which your textbook uses the gravity vector, which is fine. This is the strength of the gravitational field. It is a vector. And it has two components. You make a box around this vector, and the component down the slope is g sine theta. And the component into the slope is g cos theta. Now, you might wonder, why is it sine theta? Because it's in the x direction. It's because the theta is actually over here. Now, the way I remember this, the component down the slope, the slippery sliding component is the sine, SSS. Okay, slippery sliding component down slope is sine theta. The in slope, this g cos theta, when we get to forces, we'll see how important that is. But the acceleration for this then is just g sine theta down the incline. Down incline. Now, if you happen to tilt your incline the other way, it would have to be a negative, but I like to tilt it so it's going down to the right, and then it's positive. Okay, and you'll have a number of problems where you have to work on the acceleration. And remember, if you throw something up in the air, oops, so you give it an initial velocity, it's going to rise, stop, turn around, come back down. Well, it's the same deal with an incline. If you toss something, like you give a box an initial velocity up an incline, it'll rise, stop, slow down, and turn around and come back down. It'll simply do it with a much smaller acceleration than if it was just in free fall. And so this is actually a way to dilute the acceleration due to gravity. And this is how Galileo figured out all the relationships between acceleration, displacement, and time. It was just too quick to throw things up in the air and try to observe them. So he made a nice, long, gradually sloping incline, and he was rolling little balls down, figuring out the relationships, kinematic relationships, based on this diluted gravity incline. Okay, that'll do it for this chapter.